Hi there. In this video, we're going to be talking about divergence theorem, also called Gauss's theorem. It's not so critical for us to understand how it's actually proved. The proof of this theorem can be looked in any maths textbook. So this video will focus mainly on how it's used. So what is it to begin with? Let's just say we have some kind of surface. There's our x, y, and z coordinates. And we have some kind of region in space. So that region occupies a certain volume. Okay. So what does the divergence theorem say? The divergence theorem says that if we find the divergence of some kind of vector field, right? So in this region, there is a vector field that's acting on it, whatever it may be, however this vector field looks like. So let's just say this vector field is f is equal to xi plus 2j plus z squared k. What the divergence theorem says, if we take the divergence of this vector and we find the triple integral of it, right, along this region, if we find the volume integral, so if we integrate this volume integral of the divergence of this vector field, it's actually equal to the surface integral along that same region. So this region has a volume, but it also has a surface. So if we find the surface integral along this same region where this vector is acting on, it's actually the same as finding the divergence of that vector in terms of the volume. So this is probably most easier illustrated in the form of an example. The question at this stage is probably, what's the benefit of this theorem? How can it be used? Well, here you can see that we have a triple integral. And the surface integral, this was covered in the previous video, so you can go back and rewatch that if you just need to become familiar with what surface integrals are. But we saw that they are often double integrals. So the divergence theorem allows us to convert essentially a triple integral into a double integral. And since it's a surface integral, it has to be indicated as a vector area, as we had discussed in the previous videos. So let's look at a simple example and see how this is actually implemented. What we'll do is we'll take some kind of vector field, we'll take some kind of shape, and we will find the left-hand side, and we will find the right-hand side, and show that they are equal. So the example that we'll look at is this same vector field that I've written here, f is equal to xi plus 2j plus z squared k. So we'll say that the region is a cylinder, x squared plus y squared is equal to 4. And we'll say that this cylinder is bounded between z is equal to 0 and z is equal to 4, and also bounded by x equal to 0 and y equal to 0. So what does it look like? Okay, so we'll draw our axes. So that's x, y, and z. So since this is a cylinder and we can see that the radius is 2, we can just write that. The radius is 2. And since it's bounded between x is equal to 0 and y is equal to 0, that means that we have some planes here. Sorry, this is the x-axis and that's the y-axis. Okay, and that's the other plane. And also z is equal to 4. Okay, and of course it's a cylinder, so it looks something like that. Okay, so we essentially have a cylinder in the first octant between z is equal to 0 and z is equal to 4. So we want to apply the divergence theorem to a vector field that is acting within this region here. So we saw what the divergence theorem actually is. So we'll first define the left-hand side. So to begin with, we have our vector. So we'll find the divergence of the vector. So the divergence of the vector is this operator nabla with the dot product of the vector itself. So you would write day x I plus day y j plus day z k, and f is given to us. So that's xi plus 2j plus z squared k. Of course, it's the dot product, so I times I gives us 1, and the rest of it, perpendicular vectors multiplied with the dot product, give us 0. So what we're left with is day x with respect to x, so that just gives us 1. Day y 2, okay, that's going to give us 0. And day z with z squared, so that's going to give us plus 2z. Okay, so this is the divergence of this vector f. So what do we want? We want to integrate now this divergence and do it as a triple integral with respect to the volume. Okay, so that's a fairly simple thing to do. So we're now going to integrate over the volume of this divergence, which is 1 plus 2z, with the volume. And how do we get that? Okay, so since it's a cylinder, we're going to use cylindrical coordinates. So we just take a volume element. So you would remember when we did cylindrical coordinates, how we actually take the volume element. So we have dz, dr, that's here, dr, and we have r d theta. So the volume element dv is equal to r d theta dr dz. So we can just substitute that in, and we can, since we're integrating with respect to theta, r, and z, we can put in those integration boundaries. Z is going from 0 to 4, we can see that quite easily. R is going from 0 to 2. And since this is the first octant, this is 90 degrees. So theta is going from 0 to pi over 2. So we can just put in those things. We can integrate z going from 0 to 4, theta going from 0 to pi over 2, and r going from 0 to 2. And we're integrating 1 plus 2z. That's the divergence of f, and that's being multiplied by dv, and we have an r inside here already. So r multiplied by this, the divergence, gives us r plus 2rz. And that's being integrated with respect to dr d theta and dz. So if we integrate this, this is a straightforward integral. So we get 0 to 4, that's the boundary of z, 0 to pi over 2, that's theta, and then integrating r, we're left with half r squared plus r squared z, integrated from 0 to 2, d theta dz. So that gives us, we just write the boundaries again, 0 to pi over 2, and then substituting in 2, get 2 squared is 4, 4 divided by 2 is 2, and 2 squared is 4, so we have 4z, and we're integrating this with respect to d theta and dz. So we can proceed in this manner and carry on evaluating this integral. It's very easy at this stage, and I'm sure you're able to do it quite well. But if you carry on doing this, you'll end up with the answer of 20 pi. So you can check the steps in between that you get to this answer here. So this becomes obviously 2 theta and then 4 theta z, substituting pi over 2, then integrated with respect to z, and then substituted in 4. You'll see how you get this answer. So that is what actually this left-hand side of this divergence theorem actually tells us. So we see that this is 20 pi, okay, for the left-hand side. So the question is now, according to the divergence theorem, if we do that for the right-hand side, we should get the same answer, okay? So that's what we're going to do. We're now going to... So we have to now find the surface integral of this vector acting in this region. So if we look at this region that we have drawn and we try to identify the surface, we see that there's actually several surfaces. It's just not one specific surface. And also, as part of finding surface integrals, you'd remember that we have to look at the normal vector. You'd remember that ds is a vector area, and it's actually equal to the normal vector multiplied by the surface. The surface ds is just the normal surface area element. So we have to find normal vectors associated with all these various surfaces. So let's identify firstly what these surfaces are. Well, we have firstly the bottom of this quarter of a cylinder, and the normal vector is actually pointing out, so it's pointing directly downward. So this normal vector is actually minus k. This is the z direction, since it's the z-axis, and k is the normal vector in the z direction, and since it's pointing downward, it's minus k. So we call this surface 1. And then, of course, we have the top of the cylinder, and we'll call that surface 2. And this normal vector is actually k. It's pointing in the positive z direction. We'll call that surface 2. And then we have on the left-hand side, we have this rectangle. So this is another surface. Okay, it's a rectangle. And the vector that's pointing out actually looks something like that. So this is pointing now in the negative y direction. So it's minus j. We'll call that surface 3. Then also we have another rectangle. You can see that on the right-hand side. So you get the idea. And that's also pointing outward, and it would look something like this. So we can see that this is the positive x direction, so that's the negative x direction. The normal vector here is minus I, and we'll call this surface 4. So the last surface area the last surface that we have to look at is actually this outer edge of the cylinder, right? So it's something like this. So that's the outer edge of the cylinder. So this is pointing outward, right? So that just has a normal vector. And since it's pointing in space, it's actually n. And you would remember from the previous lecture that, or the previous videos, that it's actually the gradient vector of this scalar function divided by the magnitude of it. So we'll call this surface 5. So we have to now compute the surface integrals for these 5 surfaces. So it sounds like a lot of work, but it's not actually. So we'll just look at it, and you'll see how it simplifies quite a bit. So surface 1, what was surface 1? So surface 1 was actually the base of the cylinder, and at the base of the cylinder, you can see that there's no z value, right? So z is equal to 0. And let's just remind ourselves what our vector is that we're considering. So f was equal to, just go up to it, so it's xi plus 2j plus z squared k, right? So z is essentially equal to 0. So for surface 1, since z is equal to 0, this vector has now become simplified to f is equal to xi plus 2j. So there is no k component since z is equal to 0. So if we now compute the surface integral for that, so we want the surface integral for surface 1 of this vector, and of course we're doing ds, and you know that this vector area is actually the normal vector multiplied by the differential surface area element. And of course our normal vector is actually just minus k. So we have the integral along this surface 1 of xi plus 2j, and now multiplied by the normal vector, which is minus k, times ds. And what does this give us? This gives us 0. It gives us 0 because we're taking the dot product. You can see that the dot product is there, and when we multiply perpendicular vectors in the dot product, they give us 0. So as I was saying earlier, we have a lot of surfaces, but we can see that it's becoming very easy to find the surface integral for some of these surfaces. So let's carry on now with it, and we'll do surface 2. So surface 2, we can remind ourselves that this is actually the top of the cylinder, and at this plane, z is equal to 4. So we have to substitute z is equal to 4 in our vector. So z is equal to 4. And what that means is that f is now equal to xi plus 2j plus 4k. Sorry, 4 squared is 16. So we have 16k. So we now find our surface integral for surface 2. That is our vector dot product with the normal vector times our surface area element. And the normal vector for surface 2 we actually saw was just k. So we substitute k in. So putting all of this information in, we're taking the surface integral along surface 2 of f, and that's xi plus 2j plus 16k, dot product with our normal vector, which was k, times ds. And of course, dot product, so only k times k has a value, which is 1. And then we have the 16 there. So this entire integral basically simplifies to just 16 integral of 16 ds along surface 2. And what is surface 2? Surface 2 is actually, well, there's our circle. This is a circle. And surface 2 actually corresponds to just quarter of a cylinder. If we look at the top of it, we can see that this entire thing is just a quarter of a circle, since it's in the first octant. So the area of this portion, surface area, is just pi r squared, and the radius of the circle is 2. We're given that in the problem. So pi r squared, so this is just r is 2, so we have 4 pi, okay? And since it's a quarter of a circle, we have to divide it by 4. So quarter of the circle, the area is just pi. So what this means is that we have 16 times this surface 2 times ds, and we just saw that this part is equal to pi. So this integral, the surface integral, is actually 16 pi. So that is surface 2. So we can carry on in this manner. For surface 3, we have y is equal to 0. We can just remind ourselves what surface 3 is. So surface 3 corresponds to this rectangle, and we can see it's actually on the x-axis. So there is no y value, that's why y is equal to 0. And looking at surface 4 as well, we can see that it's on the y-axis, and we can see that x is equal to 0. So the normal vector associated with surface 3 was minus j, and the normal vector associated with surface 4 is minus I. So So we're just going to do surface 3 and surface 4 now. It's fairly straightforward. So for surface 3, we put y is equal to 0, and also we know that the normal vector was equal to minus j. So if we do our surface integral along surface 3, we have f dot normal vector times surface area element, and then putting in our vector in, so that's xi. And remember that y is equal to 0, so it doesn't really change anything because we have 2j in here from the question, and z squared times k. And we're multiplying this by our normal vector, which we saw for surface 3 was minus j times ds. And as before, the product of the perpendicular components give us 0, so we're only really multiplying j and j, which give us 1, and minus and 2 gives us minus 2. And what we're left with is ds. So this is actually just the area of the rectangle. So ds will be the area of the rectangle that we see. So it's essentially length times breadth. So the it's essentially 2 times 4, which is 8. So that's 2, and that's 4, and 2 times 4 is 8. So ds is equal to 8. So we have minus 2 times 8, which is minus 16. We just have 2 sides left, so that would be side 4. And this is where x was equal to 0, so that's another rectangle. And the normal vector was equal to minus I. So in our vector, so if n is equal to minus I and x is equal to 0, so there is no x component, x is equal to 0. So what we're left with is this, the j and k components. So yeah, f is equal to 2j plus z squared k. So proceeding with this integral, so the integral along surface 4, surface integral, is f dot ds times the normal vector. So that is equal to integral along surface 4 of 2j plus z squared k dot the normal vector, which is minus I, times ds. So this gives us 0 because minus I times perpendicular components all give us 0. So we're left with 0 here. And then we just have one more side left. And that side is the outer area of the cylinder, that is the curved part of the cylinder. So this part of the surface, right? So we have done this in the previous videos, how we find the surface integral, and we have done it for this specific example. And we saw that the procedure is that we have to firstly find the normal vector. So we have to create this gradient vectors, find all of these things, find the normal vector, find the surface area element, and then proceed with that integration. So we'll just do a very simplified, summarized version of that integration because it's done in detail in the video in surface integrals. So for surface 5, we have x squared plus y squared equal to 0. And since we have to create an implicit function, we can say minus 4 equal to 0. And we can now call that phi. That's our implicit function. And we have to find the gradient vector of that, and that gives us 2x plus 2y. And then the magnitude of the gradient vector is the square root of what we have just determined. So that gives us 4x squared plus 4y squared. So we pull out the 4 as a common factor. So square root of 4 is 2. So we have 2 into x squared plus y squared. So x squared plus y squared in the problem, we can see that it's equal to 4. So this entire thing in square root is just 4. So we have the square root of 4 again. And we have 2 times 2, which gives us 4. So if we were to now find the normal vector, the unit normal vector. That is, of course, the gradient vector divided by the magnitude of the gradient vector. And we see it's essentially 2x plus 2y divided by 4, so that's a half. So we have a half into xi plus yj. So my apologies, I forgot the I and the j here. Okay, so now that we have the normal vector, we can now proceed with our integration. So as before, we find the surface integral along surface 5, and that's the vector multiplied by the normal vector multiplied by ds, the surface area element. So that's the integral along the surface 5, and f, as we know from the question, is xi plus 2j plus z squared k, and dot product with our normal vector, which we have just determined here. So that half, we can just pull that half to the front maybe. Don't really need it. So what's left is xi plus yj times ds. So just doing this multiplication, I times I gives us 1. And of course, the perpendicular component is giving us 0. So what we're left with is a half into the integral along surface 5 of x squared, so x times x, plus 2y ds. So since we're integrating along the surface, and we will use the same method that we had done in the previous example that we had done on surface integrals, so please refer to that video to remember how we did that integration. But essentially we'll use cylindrical coordinates again, so where y is equal to 2 sine theta and x is equal to 2 cos theta. So 2 is the radius of the circle, and our surface area element was equal to 2r, this is what r is, times d theta times dz. And of course, theta is going from 0 to pi over 2, and z is going from 0 to 4. That was given in the problems earlier, so we can see that in the figure itself. We can just remind ourselves that z is going from 0 to 4, and theta is going from 0 to pi over 2, 90 degrees. So proceeding in this manner, it's a fairly straightforward integral to evaluate at this stage. So when we do that, we have the integral of f dot n dot ds, that's our surface integral definition. And now putting all of these things in, we have half into our double integral, z going from 0 to 4, theta going from 0 to pi over 2, and we have x squared. So x is equal to 2 cos theta, so x squared will be 4 cos squared theta. And we have plus 2y, so y is 2 sine theta, so we have 4 sine theta. And of course, ds is 2 d theta dz. So this is multiplied by 2 d theta dz. So if we find this integral, so all we're needing to do, that's really maybe a little complex, but we can look up a standard integral for cos squared theta. So if we do that, we can replace cos squared theta, and we can do some simplifications. We can link the half, the 4's here as a common factor, and the 2, and we can basically write cos squared theta in terms of double angles. So that's what we'll do. So that would be 1 plus cos of 2 theta, then plus 2 sine theta, d theta dz. So all we just used was double angles. So you'll remember what the double angle formulas are. You can revise it if you'd like. So cos squared theta minus sine squared theta is equal to cos 2 theta. And sine squared theta is 1 minus cos squared theta. So you have cos squared theta minus 1 plus cos squared theta. So we have 2 cos squared theta minus 1 equal to cos 2 theta. So we just solve for cos squared theta, and when we do that, we get cos squared theta. So this is a square, not a 2. Cos squared theta is equal to, dividing everything by 2, we have half plus half cos 2 theta. So we've essentially substituted this into here. So carrying on with that, integral of z 0 to 4, and then we integrate this. The integral of 1 with respect to theta is just theta minus sine of 2 theta divided by 2. That's what the integral of cos 2 theta is. So that's going from 0 to pi over 2. And then we have minus 2 cos theta. Maybe I should write it like that. So zero to pi over 2, then dz. So this is equal to 2 into the integral from 0 to 4. Of course, we substitute in now pi over 2 instead of theta, and then 2 times pi over 2 is just pi. Sine of pi is actually equal to 0. Then cos of 2 pi is also equal to 0. So we carry on like that. So what we're left with is pi over 2 plus 2 dz. Of course, the cos of 0 is 1, so we have 2 times 1, and minus and a minus gives us a plus, so that's where the 2 comes from. So integrating this, what we're left with is 4 pi plus 16. So if we now add the surface integrals of all our things, so S1 plus S2 plus S3 plus S4 plus S5, we add up all of these surface integrals. So we know that the last one is 4 pi plus 16. So what were the others? So let's just go up and see what the others were. So S5 was equal to 4. No, sorry, S5 was actually what we had just determined. That is the normal vector. So S4 was equal to 0. So S4 was 0. S3 was minus 16. S2 was 16 pi. And S1 was 0. So putting all of these numbers in, we're going to add them up and see what we get. So S1 was 0. S2 was 16 pi. S3 was minus 16. And S4 was 0. So if we add up these things, minus 16 and 16 gives us 0. 16 pi and 4 pi gives us 20 pi. So the integral along the surface of f dot ds gave us 20 pi, right? So what did the divergence give us when we took the volume integral? We go up to where we had calculated it, we see that this was our divergence, the volume integral, and we see that it also gave us 20 pi. So this was essentially an application of the divergence theorem, how you determine the triple integral of the left-hand side, and you find the divergence and you take the volume integral, and on the right-hand side you find the double integral, the surface integral. So what this is saying is that you can do one or the other to achieve a certain objective. Sometimes you can even convert the integral depending on which method is easier to use, and you can actually simplify some of these equations in this manner. So thank you for watching. The remaining videos will address Stokes' theorem and Green's theorem.